Okay, today's video is the first attempt at a Unit 5 physics run through. So this is October 2022. So obviously a lot of students in year 13 are preparing for their Edexcel International A-level, and Unit 5 will be the main exam for this May or June. It'll probably be in June, this exam. So it's on thermodynamics, radiation, oscillations, and cosmology. Okay, so just a quick plea to please subscribe if you haven't done so already, and like and share the video so we get more coverage, so it will help more people in the future. Okay, as usual, the first 10 questions will be multiple choice. Just align the video for you. Okay, so the first question is about fusion and fission. Fission and fusion are both nuclear processes. Which of the following statements is correct for both processes? Okay, so the answer is B, because A says no harmful radiation is produced. Well, that's not true, because you do get radioactive isotopes produced when you have nuclear fission, and possibly even when you have nuclear fusion, you may produce some isotopes which are radioactive. C says very high temperature is required. That's only true for fusion, so it's not true for both, and the process can occur spontaneously. Well, to me that's a little confusing, because I don't think fission is spontaneous, because if we're talking about fission to do with uranium used in fission reactors, you probably know that it's stimulated or triggered by a neutron. So anyway, D was confusing, and C, very high temperatures we've been through, so the answer is B. And two, you're basically making more stable nuclear structures. Okay, I put at first, but it's any nuclear structure. If you're making something more stable, the binding energy increases, because binding energies, if you define it, is the amount of energy required to separate the nucleons into individual protons and neutrons. And obviously that's what binding energy means. So higher binding energy means it takes more energy to split it up into its constituent parts, which are protons and neutrons. Okay, so if you're making something more stable, the binding energy increases, and in both fission and fusion you're making something more stable in theory. Okay, question 2 is about the pressure law. Okay, so the pressure law, if you know, is P1 over T1 in its simplest form is equal to P2 over T2. That's from GCSE. States that if certain conditions are met, well, what are the conditions for the pressure law? At constant volume, obviously for a fixed mass of gas, that's what they normally say. So the pressure exerted by an ideal gas is proportional to the temperature of the gas. Okay, so this is mathematically correct. Which is not correct from these 4 statements? The absolute temperature must be used. That is correct. You must use it. It only works in Kelvin because you want it to start at absolute 0. The molecules must be identical. Well, that one I don't see whether that's relevant. So this one seems to be the one that you can get to by eliminating the others. The number of molecules in a gas must stay constant. Yes, because you have a fixed mass of gas. And if you have a fixed mass of gas, that means the number of molecules mustn't change. And then the volume of the gas must stay constant. Yes, because remember, P is directly proportional to T, and the constant is N, number of moles, which is equivalent to the number of molecules, and V, these are the constant proportionalities. If you plot a graph of P against T, this will be the gradient. Okay, so this must all stay constant. That's question 1 and 2 done. Question 3 then is about a radioactive source, and it's placed a few centimeters away from the detector, so it could be a Geiger Müller tube. When a sheet of paper is placed between the source and the detector, there is no change in the count rate. So that means if a piece of paper is placed, it can't be alpha. Yeah? So anything with alpha in it, you can eliminate. When a lead sheet of thickness 0.5 centimeters is placed between the source and the detector, the counter rate is reduced to the background count rate. Okay, so which of the following is emitted by the source? So alpha can't be this, beta and gamma would still be able to get through. Some of the gamma would still be able to get through 0.5 centimeters of lead, because you need a slightly thicker bit of lead to stop all of the gamma. So it's very difficult to stop all the gamma. So really it's going to be C, which is beta radiation only. Obviously a thin bit of metal will stop all the beta. Okay, so it must be there's beta only, because if there was gamma radiation, which is A, B and D, then there would be still some going through, so it wouldn't get back down to the background count. There will still be some extra due to the gamma. Question 4 is about the Hertzsprung-Russell diagram, which they've given you here. They've given you temperature in the middle. It has an incomplete temperature scale. Well, the temperature scale you should know. They want you to know that you know the basics. As you go this way, the temperature scale, decreasing temperature. And it's a logarithmic scale, it's not a linear scale. So which row of the table gives possible values for x and y? So you want x to be higher, because you want to go decreasing temperatures as you move to the right, and y to be lower than 6,000. So there's two of them. Could be that. Decreasing temperatures at y would be these two, so it will be 3,000 at y. But then it's not linear, so it won't be 3,000, 6,000, 9,000, so it has to be D, because that's the only one that's not linear. Okay. Question 5. Radioactive decay of a nucleus is described as a random process. Which of the following is a reason for this? That means which one explains what a random process is. There are a number of different decay paths. That's nothing to do with it, and the nucleus will probably decay over one half-life. Well, the rate of a nucleus, so we're talking about one nucleus, would decay after one half-life. That's just a probability of decay, so we don't know whether this nucleus will decay after that. Okay, and C, the nucleus will decay without any external stimulus. That's true, but it's not the meaning of random. That's the meaning of spontaneous. Okay, spontaneous means there's no external stimulus, it just seems to happen. Well, as far as we know, there's no external stimulus. There is a fixed probability of the nucleus decaying in the next second. Yeah, so that would be random. There is a fixed probability. That could be any of the nuclei can decay. We don't know when, but we know it's a random process, so at any time any of them can decay. It's a bit like throwing dice. If you throw a large number of dice, there's a possibility that any of them can come up 6, but you don't know which one will. Okay, that's the meaning of the word random. So really they're just trying to see what you understand by the term random. Question 4 and 5 is done. Question 6 is about redshift. So, question 6 about redshift. Just going to move the paper slightly to the left. Okay. The graph of redshift against distance in meters was plotted for a range of nearby galaxies. The value of the gradient of the graph was 5.4 times 10 to the minus 27. Which of the following expressions gives a value for the Hubble constant in seconds to the minus 1? Well, if they plotted for a range of the redshift was plotted, well, redshift means Z, which is the ratio of velocity against c. Now, normally the gradient, if you want Hubble's constant, would just be velocity against distance, not velocity against c. So the gradient here would be the amount of shift of the velocity with the velocity over c divided by the distance. Okay, so let's just say it's the change in velocity over the time taken. So you don't really need a delta, v over d. So if I get rid of the deltas, it makes it easier. So redshift means v over c. So now instead of being v over d, it's v over c d, if that makes sense. Hubble's constant would be v over d. So you can replace the v over d by h naught over, and therefore the gradient would be h naught divided by c, which means if you rearrange it, h naught will be the gradient of this graph multiplied by c, and the gradient for this graph is 5.4 times 10 to the minus 7, and we know c is 3 times 10 to the 8, so we're looking for this number multiplied by the speed of light. So the answer is, there you go, the gradient given above, speed of light there, so the answer is D. So that's quite a tricky question, in that normally the Hubble constant would be velocity against distance, and now they've done velocity divided by c as one of the equations given as the redshift equation. Question 7. A space shuttle of mass m is returning to Earth, which has the big mass m. So the small m is the space shuttle, the big M is the planet, in this case Earth. The space shuttle falls, it says, from a height r above the Earth, where r is also equal to the radius of the Earth. So basically it goes from 2r, from the center to the center of the Earth, to r. Okay, which of the following gives the change in gravitational potential energy? The change in gravitational potential energy of the space shuttle. Well, the change in gravitational potential energy, I'm going to show you the equations that they give you. The equations that they give you in the exam, and this is question 6. Question 6 is question 7. Question 7. For question 7, the equation they give you, which you can use, is this equation. And this is the potential, which is the potential energy of a unit mass. So if you want the potential energy, which is what they're asking about for question 7, all you've got to do is you've got to multiply this equation by, so this won't be big M in this question, and you multiply by the small m, and you'll get the equation for potential energy. Okay, so basically this is where the second mass is 1 kilogram. So this one would be any kilogram, which in this case would be the satellite mass. Okay, and to work out the change in potential, or the change in potential energy, you've got to do final value minus the initial value. So it'll be the final value at r and the initial value at 2r. So the potential is minus gm over big R for when it reaches the Earth's surface, and then the initial value is minus gm over 2r where it starts falling from. Okay, so back to the question. That's where I got the equation from. So at the Earth's surface, remember, a shuttle falls from a height r above, yeah, where r is the radius. So which of the following gives the potential energy of the space shuttle? Okay, space shuttle falls from a height r above the Earth, where r. So by falling, we're assuming it means it's going to reach the Earth's surface, although they haven't said that actually when you read it carefully. So at the Earth's surface, it would be this value. Where it starts falling from, it will be over 2r. So the change in velocity from r to the Earth's surface is minus gm over r minus, so you have to be careful with the minus signs when you put them in. I've actually taken r out and put it outside the bracket. I've not put the m in the equation. I'm using potential, okay, because it's just one less letter to write. So I've taken the r out, so this would be 1 when you take the r out. So remember, the minus sign is still outside. So both of them have the minus sign, and then there'll be 1, and this will be 1 over 2 if you take out the gm over r from each of these equations. This bracket would be the 1, this bracket will be a half. So now you just got to get rid of the minus signs. This becomes minus 1, this becomes plus half, so it's half minus 1. Put the r back in, yes. So if you put the r back in, put the r there. So I've written it here, don't know if you can see that. So if I put the r back in there, take it from there, that'll be 1 over r. So we're looking for the one which has 2r minus 1r. So the answer is A. Okay? Quite a lot of work to do on that question. So I think that's quite a tough multiple choice question. And if you get one of those in the exam and you're struggling, leave it till the end of the exam. If you have enough time, you can go back to it. Okay? It's not worth spending too much time on a tough derivation. Okay? So 7 is A, 8 is about a pendulum. So it says a seconds pendulum, whatever that means. Seconds pendulum has a period of 2 seconds. I think it just means that the pendulum oscillation times are in the order of seconds. Okay, so the equation we're talking about is on the equation sheet. Is T equals 2 pi root L over G. You can rearrange that to get T squared equals that, because what they're asking you is which of the following, A, B, C, or D, gives the length of the pendulum in meters. So once you got rid of the square root sign, it's easier to see. L is T squared G over 4 pi squared. So if they say the pendulum has a period of 2 seconds, we know T equals 2. So if T equals 2, you put the T in, that becomes 4. So the 4's cancel out. So that would cancel out with that. Then you've got G over pi squared. So G is 9.81. So C is the answer to question 8. Okay. Right, that's question 8 of them done now. Question 9 is about 2 stars, Canopus and Sirius, if that's how you pronounce them. Radiation from Sirius has 3 times the intensity of radiation from Canopus. I think they mean as observed from the Earth. Okay, the distance of Canopus from Earth is 36 times the distance of Sirius from Earth. So it's about ratios, this question, and you've got to be able to work out ratios. Canopus has a luminosity LC and Sirius has a luminosity LS. Which of the following is equal to the ratio of LC to LS? So you've got to work out LC to LS, given that one is 36 times the distance and one's 3 times the intensity. So which equation gives you intensity? It's I equals the luminosity divided by 4 pi r squared. So if you want the luminosity, you change the equation round. The luminosity will be the intensity. That means what you observe, the intensity from Earth. Yeah, intensity from Earth would be how bright it would appear to you. Okay, so we know that the intensity radiation from Sirius has 3 times the intensity. So I from Sirius is 3 times I from Canopus. So we know this, and we know that the distance from Canopus, RC, is equal to 36 R for Sirius. So 36 times the distance. Then if you put these numbers in from this equation, you put one over the other, and you put them in terms of the correct terms. LC would be IC times 4 pi RC squared, IS 4 pi RS squared. You can replace the IS with 3IC. Okay, so the IC's cancel, the 4 pi's obviously cancel, and here you've got 36 RS all squared, it should be. Okay, then the R squareds cancel. Yeah, so you're left with 36 squared, because the whole bracket is squared, and 3 on the bottom. The answer is 36 squared over 3, which is a third of 36 squared, which is C. Finally, the last multiple choice question is about damping in simple harmonic motion. So the suspension system of the car was tested by forcing the car into vertical oscillations. So you've got a forcing frequency. This is called a forcing frequency. Now, you know everything has a natural frequency. The forcing frequency was gradually increased, and the corresponding amplitudes of the oscillations were measured. Okay, so this is amplitude, yeah, and you're changing frequencies. The independent variable was frequency, and the dependent variable that they were measuring was the amplitude of the oscillations. They noticed there was a maximum amplitude of oscillation at a particular frequency f0, and that particular frequency is given here. Now that particular frequency, you should know from year 12, will be the resonating frequency or the natural frequency. Yeah, so the f0 will be the natural frequency of the car, its suspension system. Then which row of the table shows how A, the amplitude, the maximum amplitude, and F0, the natural frequency, the one that created the maximum amplitude, yeah, A0, change as the damping of the suspension is reduced. Okay, so I've put a graph, which is a common graph that you need to know, amplitude against the driving frequency or forcing frequency. This is the value. So you'll notice at a certain value, you'll get the maximum amplitude. If you have light damping, the frequency is, the natural frequency F0 is there. As you increase the damping, the frequency drops. So if you're going to decrease, it's reduced, you're decreasing the driving frequency, you're going this way. So that means F0 will decrease, and so will the amplitude. You see here the amplitude when it's heavily damped is when the amplitude increases when you reduce the damping frequency, and in both cases they would be increasing if you reduce the damping. So reducing the damping means going this way, yeah, increase maximum damping, medium damping, light damping. So if you reduce the damping, so reduced damping is going up that way, both the amplitude increases and the frequency increases, which is D. Okay, so this graph is something you need to make sure you have in your notes. Okay, natural frequency of the damp system decreases. Okay, and they're doing the opposite to that. Okay, section B. Section B usually starts with the easier questions first, and none of the questions in this exam are that easy because there's a lot of maths involved, and you have to be able to work out which of the equations you need to use from the formula sheet. So I've just taken a sip of water. So this question is about specific heat capacity. A student learns that the energy required to heat water for a bath can be 10 times the energy required to heat the water for a shower. So the energy for the bath should be about 10 times the energy for the shower. That's what they're saying mathematically. The student used the shower for 9 minutes. Well, 9 minutes, you've got to change that time into seconds. That's 540 seconds. So you can automatically start your thinking by reading actively. Underlining is active reading. This means you're taking in the information in stages, and you won't make a mistake that you've misinterpreted the question. The water comes out of the shower at 38 degrees centigrade. That means after heating. Now here they've said the initial temperature of the water for obviously the bath and the shower, the water system, it stores it at 15 degrees centigrade. So the change in temperature for the shower is 23 degrees centigrade. Okay, at a flow rate of 1.8 times 10 to the minus 5 meter cubed per second. Okay, so that's the volume of water per second. If you know the volume of water per second, you can work it out as mass per second if you're given the density, and that you should know the density of water anyway. It's 1,000 kilograms per meter cubed. So they've given you that, so you'll be able to work out how much mass you've used in a 9-minute shower. Okay, so that's all the thinking. So you're already doing your thinking when you're doing that, and I'm writing down notes for you. The student usually fills the bath. Now, so that's up to there is the shower. And here is now the bath. Okay, the student fills the bath with 160 kilograms of water at 32 degrees centigrade. Okay, it's rather a coolish bath. So the change in temperature for the bath is 32 minus 15 because it comes from the same tank. Same water supply. This time the temperature increase is 17 degrees. You've got to work out, deduce means work out, whether the bath uses 10 times more energy than the shower. Okay, so we've already looked at the data they've given us, and they've also given us the specific heat capacity of water as being approximately 4.2 or 4.18 times 10 to the 3 joules per kilogram per Kelvin. Now, per Kelvin and per degree centigrade, yes, 1 degree Kelvin, 1 degree centigrade are the same. So as long as you know the difference in the temperature in either centigrade or Kelvin, you can use this equation. So we've got to be able to use delta E equals mc delta theta, which is the specific heat capacity for each the bath and the shower. So for the bath, it's easier. Given that the mass is 160 kilograms, we know the temperature change is 17 degrees centigrade from here. We can work out that the equation, if we put the values in, 160 times 4,180, I've just written it out as full, and 17 degrees centigrade gives you a value of 1.14. Okay, so you're going to get marks for doing different parts of this question, obviously. We can look at that later if you wish on the mark scheme. So that gives us 1.14 times 10 to the 7 joules used for the bath. For the shower, given the volume rate and time, 9 minutes, you know the volume of the water is that much per second, multiplied by 540 seconds, gives you a volume of 9.72 times 10 to the minus 3 meters cubed. Now, the mass of that would be the volume of that multiplied by the density of water, which is given here. So you multiply 9.72 by 1,000. Yes, it basically gets rid of the 10 to the minus 3, so it becomes 9.72 kilograms. Well, obviously, you've only used 9.72 kilograms, whereas the bath used 160 kilograms. So you're using much less water, so it's got to be more efficient, surely. Okay. The final calculation for the shower, use of the same equation, mc delta theta, we know that it's 9.72 kilograms, the same specific capacity because it's water, and this time 23 degrees temperature rise. So although you're having a hotter shower compared to the bath, you use 9.34 times 10 to the 5 joules, whereas we used 10 to the 7 joules in the bath. So calculate that the ratio is a tenth, or the bath is 10 times more than the shower. Well, if you do that, you actually get 12.2, which shows that the bath uses more than 10 times the energy of the shower, and you will get a mark for that. Okay, here is what they give you the marks for. As long as you've used mc delta theta somewhere correctly, they'll give you a mark. If you could use the volume rate to calculate the volume, you get the second mark. So use of density is mass over volume for the third mark, and use of the ratio of the energies gives you the fourth mark, and then your conclusion showing that it's 12 times as much energy is the fifth mark. Okay. Remember, you can stop the video at any stage and to go through any bit you found difficult. I hope you found my writing is clear enough. All right, so we're now on to question 12, which is also a short question and is 5 marks. Okay, so this one requires a bit of algebra. A cylinder contains oxygen gas at a temperature of 25 degrees centigrade, yeah, so that would be 298 Kelvin, and a pressure of 1.4 times 10 to the 7 pascals, so that's the pressure. So we know it's about pressure and temperature again. Calculate the density of the oxygen gas in the cylinder. Well, we know density is a total mass divided by the volume, and they've given us the mass of one molecule. So if we know the number of molecules, n, that's present in the gas, we will be able to work out density. So we just need to know the number of molecules and the volume. Well, we haven't been given the volume, so we've got to do a bit of algebra. So we know that this has n in it, this equation. So this is from your equation sheet. Pressure times volume is equal to nkt. Well, we know from here that we can rearrange this equation to make V the subject of the equation, which basically swap places with the density. So the volume would be equal to the mass of an oxygen molecule multiplied by the number of molecules that we want to, but we don't have, what we can work out, divided by the density. Okay, so if we replace volume with this equation, do you agree that you can see that we then get P times mn over rho, P times mn over rho, equal to the right-hand side of the equation, which is nkt. Now you can see we don't need the number of molecules because they've cancelled out, yeah? So we know m, we know p, we know k, it's Boltzmann constant, and you can find that on your data sheet, okay? And we've been given a temperature, so you've got to make sure you put the temperature in Kelvin. So if we just change that around to make rho the subject of the equation, yeah, so we put rho at the top, that means PM divided by KT, if you can do changing the subject of the equation. At this stage in your physics career, your math skills should be good enough to do this. You put the numbers in, which are all given to you. Pressure up here. Mass of the one molecule, 5.3 times 10 to the minus 26 kilograms there. K, Boltzmann constant, given to you in a data sheet, and 298 was the temperature in Kelvin. Okay, put those numbers in, number crunch them with one decimal place, comes to 180.4, but you'll note that the information they've given us, two significant figures, two significant figures, two significant figures. So maximum you should say is two significant figures. So that's how you get the marks. For question 12, if you want to see the mark scheme where they gave you the marks, yeah, I'll let you stop the video and you'll be able to see how they give you the marks. I've also put my derivation at the bottom, yeah. So basically the equation I derived, yeah. So remember, you can pause the video at any stage if you missed a bit. The equation I've derived at the bottom is another equation. This will always be true, this equation, but this shows you have problem solving skills. If you can do this kind of thing under exam pressure, then you'll do well in your exam. Okay, so this is the kind of skills you require for success at A level. Okay, that's question 12 done. Question 13 is a 6-mark question, which is qualitative. That means you have to be able to write very clearly. So 6 marks. So it's talking about standard candles. So you need to know what a standard candle is. The average distance between galaxies is many times greater than the size of our galaxy. Yeah, because most of the space in the universe is empty between galaxies. Astronomers use standard candles. Yeah, so what are they? So we need to know what standard candles are to determine the distances to other galaxies. Okay, describe how astronomers determine A, the luminosity of a standard candle. So first thing you've got to explain is how they get the luminosity of a standard candle. And secondly, can then use this information to determine the distance to a nearby galaxy. Okay, so first of all, first thing I put, which is different to the mark scheme, is that standard candles are stars that have known intrinsic luminosities. So, for example, Cepheid variable is one of the stars that they look for. They know what the luminosity of these stars is. And remember, luminosity means how much power a star is giving out at its surface. Okay, whereas intensity is what you measure it to be at a certain distance. So so bits and brackets are just helping you communicate your ideas in a logical fashion. So they're not looking for these words, but it helps you get your point across. So if you use the parallax method, the stellar parallax method, which you need to have revised, to determine the distance to a nearby standard candle, the star that you're interested in, it will give you a D, a value to the nearby standard candle. So once we know, so we got for the parallax method, you can only go up to a certain distance. It doesn't work. So it basically works out the parallax method works out the movement of the star against the background stars of the nearby star, and you can see that for a nearby star, the distance between 6 months apart when between the Earth being on the two sides of the Sun. And that gives you the parallax angle, which gives you the ability to use trigonometry to work out the distance to the star by measuring that angle at the two sides of the Sun, 6 months apart. So if you also measure it's the standard candles, I should have put. So you should put the standard candles. So we should just change that now. The standard candles intensity of radiation, yeah? So when we're talking about a nearby one, where the intensity is I is luminosity divided by 4 pi d squared. So this equation is given to you. Now you don't have to write this equation down in your answer. I'm just showing you that's what intensity means, okay? So at a certain distance that we measured using the parallax method, they use D for some reason rather than R for this one. If you can also measure this intensity at the distance where you're measuring it using the parallax method too, then you have this value and you got this value. Okay, then you can use this law, the inverse square law. So this is called the inverse square law. You can use the inverse square law to determine the absolute luminosity of this type of standard candle. Okay, so once you know D, obviously 4 pi is constant, and you've measured I, you can work out L. So once you know which type of standard candle you're looking at, so for example a Cepheid variable, and you know its luminosity, then if you locate the same type of standard candle, for example a Cepheid variable, in a nearby galaxy, you're coming now to another marking point. You can then use the fact that the standard candle, that standard candles have known luminosities, yes, which we've already mentioned. So this is the same marking point that I mentioned there. So you can now use this knowledge. So that's the same marking point. You won't get marked for it twice. You can use this fact that the standard candles have a low luminosity and measure the intensity of the radiation from the second standard candle in a nearby galaxy to use, again, the inverse square law equation to calculate and determine the distance to the nearby galaxy. Yeah? Sorry, last point has been off the screen. So you can measure the intensity of radiation of the second standard candle, the one in a nearby galaxy, to use, again in the inverse square law equation I showed you above, to calculate or hence determine, which is what they've used, the distance to the nearby galaxy. Okay? Now there are alternative ways of putting this, but that's, I think, the clearest way of explaining this question. So I'll let you have time to go through this if you want to stop the video. So that's question 13, 6 marker. Now they will give you 4 marks for making any of the 4 points that I've listed. The extra 2 marks will be on the clarity of your communication. Okay, so you can't, if you're written in a muddled way, you could lose 2 points even if you've mentioned a lot of these terms in your question. Okay, question 14 is about the gravitational attraction of the moon and its effect on the water levels of oceans as they rise and fall to produce tides. Now the Bay of Fundy in Canada has one of the highest tides in the world. Okay, that means the difference between a high tide and a low tide are quite noticeable. That's probably because it's not very deep. Yeah, so therefore the volume of water, once it moves, it makes a big difference to the depth. The graph shows how the water level in one location in the bay varied with time over a 7-day period. So this is 7 days, and they want you to determine the period. Well, I looked from here, the beginning of a wave at the 0 point, because the wave doesn't start at a convenient point on the 0 point of time. So I've measured it from there. That's 0.2 on my line, and I counted how many full waves. 1, 2, 3, 4, 5, 6. Hang on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13 full waves can be measured, and it goes from 0.2 all the way to 6.9 on the scale. Okay, that's in days. So that's 13 periods, that span. Okay, so if we know 13t on the graph, you get 1 mark for showing it clearly that it takes 6.7 days for 13 time periods. So therefore, you've got to change that into hours, 2nd mark, and then divide by 13 to get the time period for 1 wave. That's the first part of question 14 done. Oh, again, I haven't shown you my video. The reason I'm doing this is I zoom in so it's clearer when you see it. It's a high quality video that I've got here, so it helps you to read the questions clearly. In the earlier videos I made, the camera I was using didn't have such good quality, so I hope you appreciate the quality of the videos will improve in time. So once again, please make sure you like and share the video so we get more people using this service. Otherwise we will end up not doing as many, okay, because obviously it takes a long time to get these answers in a way that you can read them clearly. Due to the shape of the bay, part B, the natural period, which means natural frequency, of oscillations of the water in the bay, so everything has its natural frequency, everything, Anything physical has its natural frequency. So its natural frequency is the equivalent period between 12 and 13 hours. Now we worked out that the period, the force period, due to the gravitational effect, is 12.4 hours. So this is the forcing frequency, yeah, period of 12.4 hours. And remember, F equals 1 over T. So if we know the forcing frequency, if you like, this would be the forcing frequency. If you put it into F equals 1 over T, you would actually be able to work it out as the forcing frequency. If that matches the natural frequency of your water system, yeah, then you have to explain why unusually high tides are observed in the bay, okay? So what I put is this: because the period of the tide, due to the gravitational forces, matches the natural period or frequency of the bay's water due to its shape, that's the first mark. So matching the frequencies or matching the periods, they're given periods, so I'm talking about periods. The amplitude will increase under such conditions as resonance occurs. Now I think they actually give you 2 marks for that, but I'm saying that's really explaining it. So the tide's amplitudes will be the highest on the days when the forcing frequency matches the natural frequency. So I will definitely get 3 marks. You might get 3 marks just by doing that, okay? But I'm just making sure I'm driving the point home, because I don't know what's on. As a student, I wouldn't know what's on the examiner's mark scheme. So I'm making sure I go the full hog and make sure I don't leave anything to the imagination of the examiner, okay? This is the answers that they've put, 14B, okay? So you can stop the video and see if you deserve the marks or not, okay? Remember, my job is not to tell you exactly what the mark scheme is to show you a very good way of writing your answers so you don't lose marks, okay? Remember, you can stop the video. The other thing I told people in my other video was the best speed to listen back to these videos is at 1.5 speed. So obviously I'm talking at my natural rate, and when I'm thinking I have to speak reasonably slowly so my thoughts come out lucidly. But when you're listening to it, and I do the same, I always listen at 1.5 times. Remember, if you do that, you'll get through the answers more quickly. And remember, you can just stop the video when you need, fast forward it to what you want. You may have no problem with one question, you want to spend more time on the other. So just the fact that the videos may be long doesn't mean you have to spend all that time with the video on and listening to every section, every second of it. So here, question 15. I'm just seeing how many questions there are, because I will not be able to do all the video, all the answers in one video. It's 20 questions. So we'll probably stop after question 15. So here we got an observed galaxy. This galaxy is one of the most distant galaxies in the universe. A redshift Z of 10.96 has been detected by the Hubble Space Telescope, HST, by the radiation from this galaxy. So Z is delta lambda over lambda. Why am I using that formula? Because remember, there's more than one equation for the Hubble equation. So the Hubble redshift, yeah, so you're using question 6, the redshift can be Z. You can use any of these. Remember, in question 6 we also use this equation. So they're actually using quite a few equations, and by the way, this is my explanation of additional information which you can add to your notes, and I think this is quite a good way of using your formula sheet as a place of making extra notes while you're doing an exam. So I'm using this one because they've given us some information about the wavelength shift. Okay, so question 15. So they've said the radiation wavelength of 140 nanometers was emitted from the galaxy. So GNZ11 is the galaxy. So 134 nanometers is 134 times 10 to the minus 9 meters. We know Z must be the shift in the frequency that you observe, how much do you observe, against the emitted one, which is given as that. So this is the emitted wavelength. Calculate the wavelength of this radiation when it is detected at the Hubble Space Telescope. So this is a detected frequency. So we know the difference between lambda and lambda naught is delta lambda. And we know the equation from the formula sheet which I just showed you is that. So first you've got to work out that it's lambda naught is what we want. So we know Z on the left hand side, 10.96, must be lambda minus lambda naught, which is delta lambda on top. So lambda naught minus that, and that divided by lambda, which is 134. You just have to expand it then. So it becomes 10.96 times 134 nanometers. So you got this on one side, this has come to there, and then lambda naught minus that. Now this is the 11th one of these, 10.96. So it's another one of these that goes on the other side. So it basically becomes 10.96. Add this to both sides. Add this to both sides, you get 11.96 because 10.96 of these. Another one of these goes on that side. It becomes, you add it to both sides, you get 11.96 times the lambda that you've been given, and you'll find that lambda naught is 1.60 times 10 to the minus 6 meters. Okay, so the observed wavelength is that, yeah, which is way different to the emitted. So this is the emitted and this is the observed. Okay, the detected one versus the emitted one, quite a big difference. Now they've drawn your graph. The graph shows how Z for the light emitted varies with distance. So here's the distance in 10 to the power of 9 light years. Here's the Z. So they've plotted it. And so they're saying this graph from a galaxy varies with distance, yeah? And we're going to use this. A light year is a distance traveled by light in 1 year. Okay, so they're giving us that. Well, ours had a Z value, so this is a logarithmic graph. You see, it doesn't go up in a linear fashion. 0.1, it goes up in powers of 10, multiplied by 10, 0.01, 0.1. So this is a logarithmic scale. Z, for us, it was 10.96. So Z will be slightly over that line. So I've drawn a line across it and estimated the distance for our galaxy to be about 13 to 14 light years. Difficult to do. I've estimated I'm going to use 13.5 times 10 to the 9, of course, because it says so. Okay, so I'm using that because I'm going to need that in the next question. All right, so once I've done that, it says determine the distance light from GNZ11 has traveled in reaching the Earth. Okay, so the distance has traveled, yeah, is what I showed you on here. 10.96 will be slightly above that line because where is 11 on the logarithmic scale? So maybe 50 would be somewhere in the middle. So as long as you work it out between 13 and 14, they will give you the mark. The mark scheme says, yeah, anywhere between 13 and 14, as long as you use it, they will give you the mark. Okay. So we know that 1 year is this many seconds. They've used this quite a few times in this paper. D in light years from a graph is approximately 13.5 times 10 to the 9. So I've used exactly halfway between 13 and 4. I forgot to put the 10 to the 9 in. So I get 1 mark. Yes, so it's from my graph, just reading it off from the graph. 1 light year would be the speed of light times the time. Yeah, so that's speed of light, c, times the time it took, 1 year. Yeah, would be that. So this is the distance it travels in 1 year, but ours was 13.5 billion light years. So you've got to multiply 1 year distance. So that's the distance light travels in 1 year in meters. So that might be worth just noting that, taking that moment to observe it. That's the distance light travels in 1 year. Doesn't mean much to us. It's 10 to the 15 meters, nearly 10 to the 16 meters. So you multiply that, you get 1.28 times 10 to the 26. But remember the distances they're given us. Here they're given us 3, but in the question, here 3 significant figures. Here, this was very approximate. So I think 2 significant figures is all you need. So I've rounded it up to 2 significant figures. And that's a trick that you need to be aware of. That's the 3rd mark. Okay. And finally, before we take a pause, for the last part of the question. The recently launched James Webb Telescope, which was put up recently a few years ago to replace the Hubble Space Telescope, it's much more high quality images, is designed to operate in the infrared region of the spectrum. Okay, let me just go back and go through this. Now, the visible range of wavelength is 10 to the minus 7 meters. Yeah? Well, this is smaller than 10 to the minus 7. It started out as 10 to the minus 7. It ends up at 10 to the minus 6. Okay, so before 10 to the minus, longer than the wavelengths of red would be infrared. So we're talking about wavelengths which are longer than red. So the James Webb Telescope is designed to operate in the infrared region. Okay, explain, it says, why this will be helpful for certain distant galaxies. Well, very distant galaxies are receding the fastest, so they will have very large redshifts. And if they've got very large redshifts, the delta lambda will be large, and the lambda naught that you'll be detected will no longer be in the visible range. So if they're not in the visible range, they become longer, they'll be in the infrared range. So their visible light, from the distant galaxies, will have become so redshifted and it falls into the infrared region of the spectrum when it arrives at the telescope. So it allows you to observe light from distant galaxies. So it's important that they are measuring in the infrared region. So that ends question 15, and I'm going to take a pause there, and we got questions 16 to 20 to do. So if you find that useful, please, once again, a plea, like and share the video with any friends you know who are doing a similar exam, and please subscribe so you know when the next video is done. Also, if we get enough subscribers, then YouTube actually may end up paying us for doing these extra videos, and that's the ultimate goal, to actually get this to be useful globally. And obviously we're not going to do them forever if we don't get any compensation. So thank you very much for watching. Hopefully see you in the next video. Bye for now.